take a look at inverse functions. Go to my tablet here. And before we get to inverses, let's talk about one-to-one functions. For something to be a one-to-one function, our definition is for every x, so for every x there's only one y. And for every y there's only one x. Now this is kind of a hard definition to work with, so I'm going to write a little easier definition up here. You may remember part of that from before. This first part is for the function part. For every x there's only one y. The part we added on after is the 1-1 part. Okay, our easier definition says if you have one of the following, it is not a one-to-one function. It might still be a function, but it's not a one-to-one function. If you have a x squared, x to the fourth, or x to an even power, it's not a function. If you have a y, or one-to-one function, if you have y squared, y to the fourth, y to an even power, it's not a one-to-one function. If you have the absolute value of x, if you have the absolute value of y, if you have a plus or minus square root of x or plus or minus square root of y, it's not a function. Or just more generally, if you just have plus or minus x, plus or minus y of some form. If you have x is equal to a number, it's not a one-to-one function. And if you got y is equal to a number, it's not a one-to-one function. Excuse me. Unless there is a condition put on x. So unless there's a condition put on x. What I mean by that, if you have this right here, f of x is equal to x squared, that would not be a one-to-one function. Unless you see something that looks like this. X is greater than or equal to 0. They'll put a condition on here to make it one-to-one so we can actually work the problem down. Now there's also a graphical way to tell. Now this what we're going to look at here is for the one-to-one part, not for the function part. And it's the horizontal line test. It says if any horizontal line can intersect our graph at two or more places. Wish I wrote faster. So at two or more places, it is not one-to-one. So if any horizontal line can intersect a graph at two or more places, it is not one-to-one. Now why do we even really care about the one-to-one? If the function is one-to-one, it has an inverse, which is what we're finding in this section. We're finding inverses of functions. If the function is not one-to-one, it doesn't have an inverse. So it doesn't have an inverse. Let's take a look at our first problem. And we got that right there. Okay, instructions say which graph represent functions that have inverse functions. Well, let's first determine if it's one-to-one. It's a function, so we're fine there. They, I think they tell us it's a function. Which graph represent functions? No, I guess they don't tell us a function, but it's a function. Horizontal line test. If I draw a horizontal line here, most of it will intersect one place. Here's one place. Here's one place. No matter where I drop a horizontal line, the most it'll ever intersect is one place. So this is one-to-one, which means this is implies that you see, it says which graph represent functions that have inverse functions. This one does have an inverse. So it's one-to-one, implies there's an inverse. So these are yes or no type questions. So answer is yes. Look at our second problem. And that graph right there. Well, I can draw a horizontal line right here and it intersects at two or more places. Now again, a horizontal line test says if any horizontal line can intersect a graph at two or more places, it is not one-to-one. So this one is not one-to-one, which implies there's no inverse. So the answer here is no. Well, let's look at what is an inverse graphically. And we'll use this graph to do it. Okay, so we got 3. And it looks like one of our points is at -4, 0. So it's right there. Next point is at -1, 1. -1, 1. Which is right there. And then there's another one at 1, 2, 3, 1, 4 maybe? Right there. And it's draw a line like that. And like that. Right here, passing at a 45-degree angle, is the line y is equal to x. And inverses are symmetric to y is equal to x. Well, let's see what that means. Now this this point here is -4, 0. Our inverse will be those points flipped around, so it'll be 0, -4, which would be right here. Now this point is -1, 1, so our inverse is going to be those points flipped around, which is 1, -1, which is right there. And this point is 1, 4, and again our inverse is that point flipped around, which would be 4, 1, which would be right here. Okay, so if I connect those together, excuse me. I don't draw that very well, but if I was a little bit more precise, this should have been over a little bit more, then you would see that it's symmetric to this. Basically, you can eyeball it. You can take this part of the graph here and you can flip it across this line and it'll give you that part. Well, this right here is our inverse, and it's written with this notation. Over here, this would be our f of x, and it looks like f to the negative 1 power. That's not f to the negative 1 power, that's our inverse notation. But that's what you want to do in these ones where it says use graph of f to draw the graph of its inverse. Well, let's take a look at what an inverse is algebraically. And I hope I am... yeah, I don't need those. And let's come up here. So let's look at a definition of an inverse algebraically. This says f of x and g of x are inverses if the composition of f and g is equal to x and the composition of g and f is equal to x. Now both of those have to be true. And that actually kind of makes sense when you think they're symmetric to the line y is equal to x, that these both will equal x. So let's look at a couple problems to help us determine if they're inverses. So here I got f of x is equal to 9x minus 1, and g of x is equal to x plus 1 over 9. And instructions say find f of g of x. They've already put that in function notation for you. And g of f of x. And determine whether each pair of functions f and g are inverses of each other. So determine if they're inverses of each other. Well, we have to find the composition going both ways. So we're going to find f of g. And remember, we take our f of x, where we have a x, we put in parentheses. And we're going to plug in g, which is our other function, into the parentheses. So I put x plus 1 over 9 in there. Now the 9's cancel here. And we got x plus 1 minus 1, and 1 minus 1 cancels, and we got x. So that's the first part. Second part is we want to find the composition going the other way, composition g and f, which is g of f. And we'll take our g of x, which is x plus 1 over 9, and where x was, we'll put in parentheses. Now again, whatever's inside the parentheses here is what we're going to put in right here, which is f, which was 9x minus 1. Well, a negative 1 plus 1 cancel, and we got 9x over 9. The 9's would cancel, and we just got x. Since both of those are equal to x, these are yes or no type questions, I think. Determine whether each pair, the answer here would be yes. They're not yes to just, I mean, this entire thing is your answer. It's a proof, basically. Let's take a look at another problem. Okay, so we got f of x is equal to 5x minus 2, and g of x is equal to x plus 5 over 2. And the question is if they're inverses of each other. So again, I'll find a composition going both ways. Composition of g and, or f and g, which is f of g. So I'm going to take my f of x, and where my x is, I'll put in parentheses. And whatever's inside these parentheses, we're going to plug in here, so which is g. But g is x plus 5 over 2. Well, let's see. Multiply the 5 through, so 5 times x is 5x. 5 times 5 is 25. Over 2, excuse me. Something didn't agree, 8 didn't agree with me. Okay. Now, I want to merge these into a single fraction, so I'll put that as 2 over 1. Get a common denominator, which would be 2. Now I multiplied the bottom part by 2, so I have to multiply the top part by 2, so that'd be 4. At some point, you're going to recognize that there's no way that's ever going to give you x. You know, as I put that into a single fraction, it's nowhere even close. So at the point where you recognize that it's not going to give you a single x, those are not inverses. Because again, both of them have to give you x. Let me start a new page here. Let's take a look at how to find an inverse. So finding an inverse. I'll put a note up here. Your function must be 1-to-1. When I first started teaching 17 years ago, I started working a problem, and I didn't read directions very close. And they said find the inverse, and that's what little I read of the instructions. So I started working a problem, and I was working and working. It's a lot of steps, and I'm thinking this has got to be the hardest problem I've ever seen for an inverse. And so then I went back to the book after I got done working the problem, and I looked at the instructions and said, first determine if the function is 1-to-1. If it's not 1-to-1, don't even work it. I shouldn't have been working a problem. And that's what basically, occasionally you'll run across a math book where they'll throw in trick questions. They'll put one in there and they'll say find the inverse, and it's not one you should be finding inverse on. Okay, first step. Replace our function notation f of x with y. Step 2, interchange x and y. Step 3, solve for y. Step 4, replace y with your inverse notation, what looks like -1 power. And if necessary, make your inverse. What do you want, Eric? Make it quick. I'm recording. What?
I fixed the problem. Yes, we know it when I was going to tell you. And by the way, those chips good?
Chips.
The chips that you bought yesterday.
Yeah, you can eat them.
They're good chips.
Okay, so step 5. If necessary, make our inverse function 1-to-1. Use graph if necessary. Just use graph. I thought it might be something important the second time you came in. House was on fire or something like that, but sorry if you eat chips. Okay. Someday I'll build my Fortress of Solitude up at the North Pole, and I won't have my wife or kids coming in. Let's take a look at number 6. Find the inverse of this. Okay, so first step, replace f of x with y. So put y in there. Now step 2, interchange x and y. So where the y is, we'll put an x, and where the x is, we'll put a y. So swap them out. Step 3, solve for y. In this particular problem, we'll take -3 to the left side, becomes a +3. And then we want to divide both sides by 5. We're going to do that, because 5 is going to cancel. And we got y is equal to x plus 3 over 5. Now step 4. Replace your y with your inverse notation. Like that. Now step 5 says if necessary, make our inverse 1-to-1. Now remember the list of items we had that we they'll give us problems, the x squared, x to the 4th, y squared, y to the 4th. If it doesn't have any of those, you're fine. And we're fine here. This would be our answer. Let's take a look at another problem. Let's see, this is 7. We've got f of x is equal to x plus 3 to the third power minus 2. Okay, our first step is replace f of x with y. I'll put that in. Step 2 is to interchange x and y. So this becomes x equals y plus 3 to the third power minus 2. Now step 3 is to solve for y. So I take negative 2 to the left side, becomes a positive 2. We're trying to get y by itself. Now we looked at this in a previous section. If you got a fractional power, you can raise both sides to the reciprocal of this. Well, if I were to put this into fraction form, it'd be 3 over 1. So we're going to take both sides to the 1/3 power. Well, over here, the 1/3 power is the cube root. And over here, 3 times 1/3 gives us 1. They cancel each other away. We're left with y plus 3. I'll take 3 over the left side, so we get negative 3 plus the cube root of x plus 2 equals y. Now step 4, put your inverse notation in. So our inverse of f is equal to negative 3 plus the cube root of x plus 2. Now, this is not one of our items in our list that causes us problems. We had square root, and actually it's any even index. We have a plus or minus before it. Now, if you have an odd index like this, even a plus or minus 0 mess it up. But we're fine here. We don't have any of those bad items. So that's our answer. Let's take a look at this next one. Every semester, somebody comes up with the final exam for the department. It's a departmental final exam, so everybody takes the same one. And one semester, I wrote it, and I put this one on the final. I didn't think it was too bad of a problem, and I think probably 99% of my students missed it. And then I heard from almost all of the instructors. They said, "Don't do that again. Don't put this on there." This was a little bit of a challenge. Let's go through it. Our first step, replace f of x with y. So I got y is equal to 4x minus 1 over x plus 5. Now step 2, interchange x and y. So we got x is equal to 4y minus 1 over y plus 5. Now step 3 is to solve for y. And this could be one place where the people start getting hung up. Whenever we've dealt with rational equations, you always, your first step for rational equations is to get rid of the fractions. So multiply everything by the LCM of all your denominators. I only have one denominator, the y plus 5, so I'll multiply both sides by y plus 5. When we do that, these y plus 5 is going to cancel. X times y is xy, x times 5 is 5x, and this is 4y minus 1. May have been the second place people faltered, but I mean, when you're solving for a variable, you get everything with that variable on one side. So I'm going to take the 4y, move it to the left side, and take the 5x and move it to the right side. Anytime you take anything across your equals, remember the sign changes. So we got xy minus 4y equals negative 1 minus 5x. Now, we have to we're trying to get a single y. We got two y's. There's two different ways you can get a single y. One of them is combine together like terms, which really doesn't fit here. The other one is to factor out a y. So I'll factor out a y. And that leaves us x minus 4. Our last step, divide both sides by what's behind our y. So we're going to divide both sides by x minus 4. And these x minus 4 is going to cancel there. And we got y is equal to negative 1 minus 5x over x minus 4. Now step 4, put our inverse notation in. Now step 5, if necessary, make it 1-to-1. This is already 1-to-1, so we don't have to worry about that. They will put something additional on this. They'll put x cannot equal to 4. They're not putting that on there to make it 1-to-1. They're putting that on there to specify the domain. Because if I put 4 in for the x, I'd have 4 minus 4, and I'd have 0 in the denominator, which I can't have. So that's my answer. Let's start a new page, and then we'll look at the next problem. Okay. We got f of x is equal to x squared plus 2. And then we got a condition on x. Now normally, this would not be 1-to-1. Since it has an x squared, a squared on there, it means we can't solve the problem. We wouldn't even do it. But since they put a condition on this, they're making it 1-to-1. So we'll go through our steps. First step, replace your f of x with y. Second step, interchange x and y. So we got x is equal to y squared plus 2. Step 3, solve for y. So I take 2 over, it becomes a -2. Square root property. If you got something squared equal to the other side, you drop off your squared and put a plus or minus square root around the other side. Step 4, replace your y with your inverse notation. That gives us plus or minus square root of x minus 2. There's a problem with this. Step 5, make it 1-to-1. We cannot have a plus or minus before square root of x. So we have to somehow make this 1-to-1. Usually your graph is going to be your easiest way to do this. Now normally, the f of x is equal to x squared plus 2. The plus 2 means my parabola, my quadratic, has been shifted up 2 places, like that. But when we have the x is less than or equal to 0, what that means is we're only keeping the left side, like that. Well, remember, if that's our function, if that's f of x, remember our inverse and its function are symmetric to the line y is equal to x. That right there. So if I take this and I flip it across this line, it'll look, what am I doing? Okay, try 2. Better go to bed. There we go. It'll look like that. Okay, so this is our inverse. Well, take a look at this. This is saying our inverse is equal to this, plus or minus. This is the same as y. So we're saying y is equal to plus or minus square root of x minus 2. But look specifically at our inverse down here. The y values down here are negative. So the answer we're going to want to keep is the negative version of that. Again, you look at your graph and you see if there's something special about your inverse that'll help you decide which plus or minus to keep. Usually on this you just drop one of them. Now they'll put something additional on here. They'll say x is greater than or equal to 2. This is a domain. This is not there to make it 1-to-1. But it's there to specify the domain. By putting the negative there, that kind of ensures that. And that'd be your answer. Let's look at our last problem. We got f of x is equal to, and sorry, I was playing with my piece of paper here. Got a piece of paper on my tablet, and I was wondering why. Boy, I got a lot of dirt underneath it. Maybe that's why I'm having trouble. There. Okay. Now this is fine. This is 1-to-1. We can't have the plus or minus before it, but we can have a square root of x. So that's fine in that regard. So let's go through our steps. First step is to replace f of x with y. Second step is to interchange x and y. So we've got x is equal to square root of y minus 3. And step 3 is to solve for y. So I take the negative 3 over, becomes a positive 3. Now we're trying to get rid of that square root, so we're going to square both sides. We've got x plus 3 squared is equal to square root of y squared, which gives us x plus 3 squared is equal to y. Now, step 4 is to put our inverse notation in. So it would look like this. Well, there's a problem with this. We cannot have an x squared, and this is a square root on the x. So we're going to need to do some looking at the graph. Now, square root of x. Then we've got a minus 3. That's shifted down 3. And it would look like that right there. Well, our inverse is symmetric to that. Now this occurs at negative 3 on my y-axis, so this is going to occur at negative 3 on my x-axis for my inverse. Okay, so it looks like that. Then my inverse will look like that, more or less. If I take this, flip it across there. So this is our inverse. And this is our function. Well, let's see what we came up with. X plus 3 squared. Well, if the number is inside with the x, remember it's shifted left or right, opposite what you think. Plus 3 would make you think it goes right 3, so it really goes left 3. And this is what the graph would look like. Well, look at what we're wanting. It looks like we kept the right side of it, didn't we? So to make this one 1-to-1, we're going to put a condition on it. We'll say it's x plus 3 squared, where x is greater than or equal to negative 2. Again, or, no, sorry about that, negative 3. Boy, my eyes are sometimes bad. Because look, here we got negative 1, negative 2, negative 3. And it looks like we're keeping the right side of the graph. We're dropping off the what's to the left. So that right there would make it 1-to-1. And that's actually the end of that section. Go see if the house really is on fire. So let me say this.